Hello, welcome back to another lecture on waveguides. So, let us quickly jump into the topic that we left in the last lecture on understanding the waveguides and how one can define different regions and also how the electric field could be propagated through this waveguide. So, particularly we are interested in slab waveguides, right. So, we will continue doing that. Let us first look at whatever we just summarized in the last lecture. So, we concluded here, so where we had the resonance condition, the transverse resonant condition, and that depends on the phase that you accumulate when the light is bouncing between the two interfaces here. So, that is the phase here 2 k 1 d cos theta, and phi 2 and phi 3 are the phase that is accumulated when you have reflection from the two interfaces that we have. So, we know from our basic understanding of reflection that this phase shift is polarization dependent, or the electric field orientation dependent. So, let us continue a little bit more into this whole reflection problem, right. So, let us look at the orientation of electric field and how you can visualize the flow of a field through this medium. So, let us look at the transverse electric polarization. So, that is TE polarization. So, again Z is the direction of propagation. So, we have this. So, this is N1 and it is clad N2. So, now the light is going to propagate through this medium like as we already saw earlier. So, now we need to mark the electric field. So, as you all know, since this is TE, your electric field is going to be parallel to y axis, all right, and your H is here and he is here, and N1 k is in this direction, all right. So, the electric field is pointing in the y direction corresponding to the perpendicular, or rather what we call the S polarization, right. So, S polarized light here. And the field here, right, what we call the TE field, this is entirely in xy plane, right. So, that is something that you should keep in mind. So, there is no z component, right. So, the field lies in xy, and that is the reason why Ez will be equal to 0. All right. So, this is propagating around z direction. So, let us look at TM polarized light or p polarized light, right. So, this is what we have. In this case, the same geometry we take, light is propagating through this, and now your H field is now in along y, all right, and now our E field is perpendicular to the propagation direction, and this is what we have as E and N1 k. So, let me write it a little bit bigger, N1 k, and here this is N1 k, all right. So, in this case your magnetic field points in the y direction, right, and for this particular polarization your H Z will be equal to 0 here, all right. So, this is the difference between the two polarization that we have and how they propagate through the system. And from here you can easily note that your phase shift is not going to be same for both TE and TM, and because of this reason the solution to TE and TM waves are going to be different as well. All right. So, so that is something that that we should keep in mind, that the solution for any slab or any waveguide structure will be different for TE and TM, in addition to the the transverse resonant condition, which is again a discrete solution. So, that is something that I want to point out here. The guided mode, so the guided mode solution is discrete. So, it is discrete. So, you cannot have arbitrary m values, right. So, it will only take integral numbers, right. So, the mode number is say 0, 1, 2 and so on. You cannot have 0.1, 0.2 as m. So, it has to be integral or integer numbers or integral numbers only, all right. So, if that is the case, right. So, that means your transverse resonance condition is discrete, right, because m values are discrete, and this results in discrete propagation constant, right. So, the propagation constant has to be discrete, right. So, although your theta c the critical angle both here in the interface between N1 and N2 and N1 and N3 does not depend on the polarization, but the phase shift depends, right, the phi 2 and phi 3, right. So, phi 2 here and phi 3 as a function of theta, this depends on polarization. All right. So, this is something that you should keep in mind, right. So, it is the solutions are discrete, right, from our resonance condition, but then your the phase shift that you get from the two interfaces is a function of polarization, right. So, there are now you are refining your guided mode solution here. It is not just discrete, but even if they are discrete, there is one more factor to it, that is a polarization factor. So, the implication here is TE and TM modes or waves have different solutions for transverse resonance condition, all right. So, this is a very important understanding that one should have, that the polarization, different polarization of these waves create different solutions, and they are discrete as well. Another important thing is for a given polarization, let us say whether it is TE or TM polarization, the angle, right, the resonant condition that you have for a small beta would corresponds to small theta, right. So, we let us go back, probably I will draw a new one that is better. So, let us take the same slab. So, the waves could propagate without any reflection at all, it is through the axis, right. So, there is no reflection at all, and then you have another possibility where you have reflection. So, the wave that is going through with the smallest angle here, the theta. So, this will have the smallest beta, right. So, you will for a larger value of m. So, beta will be increasing as a function of m. So, as the m increases, the beta decreases in this case. So, beta naught will be greater than beta 1, which will be greater than beta 2, greater than, and so on. So, this is again something that one could easily calculate, but this is what we have from our understanding here. So, you can calculate it from the angle of propagation here, right. So, there is no phase shift and the quantity here will be higher. So, the phase shift will help you to do that. So, you could have beta 0, right. So, m is equal to 0, which will correspond to beta 0, and this is the first mode, we call it, right. So, we call this is the first solution or the lowest solution, we call this as fundamental mode. Right. And when m is not equal to 0, right, anything higher, we call this as higher order mode. Okay. So, this is something that one should keep in mind, because m is giving you all the integers that requires you to index your modes, and the fundamental mode here is given as m naught or beta naught in this case, and then for m greater than 0 the modes are called higher order modes. Okay. So, these are all solutions, by the way, right. So, this could be just for Tm and for Te as well. So, this is for a given polarization, you can have this. So, you could have fundamental Te and fundamental Tm. So, if one should be even more specific, you can put beta naught Te, right, and you could also make this for Tm m equal to 0. The same thing applies here, but we call this Tm. But then this is again fundamental Tm mode. So, you could call it fundamental Tm or fundamental Te. All right. So, this is something that you can revise and then see how one can relate the discrete modes to the solutions with respect to polarization. So, now let us look at some plane wave representation of this planar waveguide. It's an interesting way to look at the propagation here, which will give us even better understanding of how light would propagate through this system. So, let us have this as D, right, N1, N2 and N3. So, the light would propagate through this like this system, and we have theta, can put theta 1 and I will have light that is radiating out, could be, let us pick a different color which will be good. So, light is leaking out this way, it could refract, could also refract here. So, now we have light that is reflecting and light that is refracting, right. So, let us put all these k vectors now, all right. So, this will be our k1, all right, and let us say this is our k3 here, all right, and we can easily draw our k vector triangle, right. So, the k vector triangle inside will be beta here, and this will be in this case h, right, and you could have k1. Okay. So, there is one way. So, I think this might be a little confusing, let me do it this way. So, this is h and this is k1, and outside again we have beta, this is K3 and this is K3x, let us say. Okay. So, there is upward field and we have downward field, right. So, whatever you have in the clad and whatever you have inside. So, the upward field is given by so upward field, let us say EU is given by E naught e to the power I k upper dot r, let us say k upper, and then so downward field here is ED, which is E naught e to the power I k d dot r. So, what is this k u and k d is? It is nothing but e to the power I h x e to the power I beta z, and this is not e to the power of I h x, this is minus because it is downwards, and then e to the power I beta z. So, where r is nothing but x times a x plus z times a z, and k u is nothing but h times a x plus beta times a z, and k d is minus h a x plus beta a z. All right. So, this is how one could represent a plane wave representation for this a planar waveguide structure. All right. It is useful when you are doing a very simple expansion and propagation here. So, the total field, right. So, E total is nothing but E up plus E down, right. So, if you add whatever we had, we will end up with 2 E naught cos h x e to the power I beta z. So, this is what you get. So, now we are getting close to defining how this field is going to look like, right. So, from our earlier understanding of how the plane wave is could be used in order to explain this propagation, and now we have a total field, right, with respect to the position, right. That is a total field will be 2 E naught cos h x times cos beta z minus omega t. So, this is how your field is going to look like. So, this is nothing but the real instantaneous field that you have here. So, if one wants to see how this field would look like, right. So, you have a certain d here. So, for a very simple waveguide, a slab waveguide like this, we can draw our modes now. So, how the field would look like, right. So, as a function of position here. So, that should look something like this. So, this is what the fundamental solution is going to look like. We call this as TE 0 mode, right. This is the fundamental mode, and now how the other solutions are going to look like. It is basically expansion of what we just saw. Oops. Let me put it so. This is TE1, this is the first order mode, and then it keeps on moving. So, now you will have a mode like this. So, this is TE second, right. So, this is how your mode is going to look like. As you can see, this is all discrete solutions. So, this is how your mode solutions are look like, right. So, because m can only assume the integral values, right. So, this will be discrete. So, that means thetas are also discrete, right, satisfying the resonant condition. So, again this will propagate with a propagation constant of beta naught, and this will propagate with beta 1, and this will propagate at beta 2. Important thing to note is this is all TE waveguide. So, this is all TE modes. We could also do same for TM as well. So, the one way of also representing this mode is through the 0 crossing that you have, right. So, we call this 0 because there is no crossing, right, across the 0 mark here. So, the field is going to decay till the end, but there is no field crossing within the structure that you have, right. So, it is symmetric, right. Drawing is not accurate here, but you can see here there is one crossing here. So, we call this as 1. So, there is no crossing, this is 0, and here you say there is 2 crossings, and here the mode number 2. Okay. So, 1, 2, this is all higher order modes. So, these two are higher order, and this is what we call fundamental mode. All right. So, next let's look at the interface here. So, we were able to plot this through this function, right. But if I go on top, so we have this interface between N1 and N3 and N1 and N2. We have studied in our basic electromagnetics, right. So, when the wave is encountering a surface, then there should be a boundary condition. So, the boundary condition we have studied is the continuity in the energy, the electric field should be continuous, right. So, the electric field vectors on both the sides should be parallel with each other, right. So, that continuity equation should be there. So, unless you have that continuity, energy will not be able to propagate through the system. So, here again we have two interface, right. So, at the middle you have wave propagating, and we have two interface, one at the top and one at the bottom. So, now the question is, if this wave has to propagate through this particular structure, then there should be a continuous energy distributed in all the 3 layers. So, N1, N2 and N3. So, there should be a continuous inner equation between these, right. So, the boundary condition should be continuous. So, let us look at what is this boundary condition, or in other words what is the phase matching. So, different waves can travel at different speeds, that we know. The waves in N1 will travel at a different speed compared to N2, right, because the refractive index is different. So, once the diffractive index is different, the propagation constant is also going to be different. But now the question is, the energy is distributed in these 3 layers. So, how is it possible that the wave will propagate through the system without disintegrating, without losing the light, all right. So, let us look at that through this phase matching condition. So, let us closely look at the interface. So, let us take the interface, just a single interface, right, N1 and N2. Let us put our k space k vector triangle here. So, beta is here, sorry, let me make it little bigger. So, this is beta, and here also we will have beta. So, to make it specific, we will put beta 2 here and beta 1, right. Let me pull this a little down. So, this is N1. So, we have beta 2 and beta 1. The next thing is we have the vertical vector, that is k1 x, and here k2 x, and then we have the propagation constant here N1 k and here n2k, right. So, this is rather straightforward, right. So, we can easily understand why we have done this. So, in the absence of one or the other, it's going to remain the same, right. So, now the phase change, right, when it propagates through n1 or n2 is going to be different, right. So, how do we make sure that the light actually continues to flow, and this is where we need to make sure the propagation constant in beta 1, propagation constant in n1 and n2 are equal. That means beta 1 should be equal to beta 2, right. So, from both on n1 side and n2 side, the wave should propagate with same velocity. Okay. So, beta 1 should be equal to beta 2, or it should be equal to some beta. Okay. This condition is known as phase matching, this interface. So, this phase matching, so what is the purpose of this phase matching? This will allow coupling, right, the coupling of oscillation field, right, coupling of oscillating field between the two media, right. So, we want to make sure that the light is confined inside one medium, in this case n1, right. So, we need to make sure that the propagation constant in n1, which is core, and the one at the cladding here, that is beta 2. So, these two should be equal, only then we can propagate the light here. So, quickly looking at this beta 1 and beta 2, let us equate this, right. So, what is beta 1? So, beta 1 should be equal to beta 2, this is what we said, right. So, what is beta 1? Beta 1 is nothing but n1 k sin theta 1, right. So, n1 k sin theta 1 is our beta 1, right. What is beta 2? n2 k sin theta 2 is beta 2, right. So, now this is really excellent, right. If you look at this equation, so you can take out k, right. So, n1 sin theta 1 equal to n2 sin theta 2. What is this? This is nothing but Snell's law, right. So, Snell's law is back here, right. So, in a completely different way of looking at this thing, right. So, we did not use geometric optics, right. That is what we normally use when we are understanding Snell's law for reflection and refraction, right. In this case, we did not do that. We actually used wave propagation and propagation vectors here. So, even with that understanding, right, we are able to I think one thing I missed here is this is theta 1 and this is theta 2. Let me just complete that, and that's where this theta 1 and theta is coming from. So, it is quite amazing that you can arrive at this fundamental concept, right, from whichever direction you come from, right. So, that is reassuring that whatever you have learned as basic can be can be arrived with even more complex ways, but giving you very simple solutions. So, we have achieved this this phase matching, let us say, right, and what will happen to this condition if the waves are not at the angle that you want, right. So, there is a critical angle that you are looking for. So, that is your total internal reflection angle, right. Let us say your phase matching at a total internal reflection angle, let us say some angle which is greater than the critical angle, right. In this case your sin theta 1 is greater than n2 over n1. In this case your beta is nothing but n1 k sin theta 1 which is equal to beta 2, which will be greater than n2 k, right. So, let us look at how that the vector looks like in our simple k space, right. So, there k2x is what we are looking at. So, it is what we already saw, right. So, n2 k the whole square minus n1 k sin theta 1 the whole square. Okay, so, this is beta, right. So, this is n2 k. I did not do much here, right. You can go back and have a look at this. So, this basically this is what you are finding k2x, right. This is nothing but beta no n2 k2 square minus beta square. Okay. So, this is something that you can do. This is just simple Pythagoras theorem, okay, where you say beta square plus k2x square will be equal to n2 k the whole square. Okay. If you want me to write, we can write it here. So, b2 square plus k2x square will be equal to n2 k the whole square. Alright. So, this is simple Pythagoras. So, we are taking that and modifying it a little bit, moving it this side. This is what you get, right. So, now the question here is, your beta 2 which is greater than n2 k, right, won't be equal to the propagation constant you have here. So, this is going to be higher. Okay. So, your n1 k sin theta 1 will be higher, right, or we can do some rearrangement here. That means n1 k sin theta I minus n2 k whole square here. Sorry, this is not I, theta 1. Okay, I do not know why I am saying this I. So, if you do this, becomes I within roots now, and this is k2x. So, now you can see that this k2x, right, the constant along x direction is imaginary now. All right. So, because this is imaginary, right, you are going to have, I can represent this whole constant, let us say as alpha. So, here alpha is nothing but n1 k inside theta 1 minus n2 k. So, this is what we have as alpha. So, one can represent this k2x as I alpha. Right. So, now how is the field going to look like along the x axis here, right. So, you want to know how the field is going to look going beyond, and that is given by the field, right, the field in the transverse direction. So, now the field in the transverse direction will look something e to the power minus alpha x times e to the power I beta z minus omega t. So, now you can see here the propagation that you have, right, when theta is greater than theta c, right. So, what we mean by that is this is the critical angle. So, anything below the critical angle you are fine, right, but if your angle is too steep, right. So, your angle is too steep, what will happen to that particular field, right. So, that field, the angle beyond which you are going to lose that light, okay, and that decay, right, how fast it would decay is something that is given through this simple relation, right. So, this is from our simple k vector representation, right, and if you just simply do reorganization here because of the magnitude of n1 k1 sin theta and n2 k, right. So, because of that magnitude you will eventually end up with an imaginary k, right. The propagation vector will be imaginary. So, what that means is it is going to be attenuated. So, this alpha that we talk about is nothing but the attenuation, okay, and this attenuation is what we call evanescent field, right. So, this field that is dying, right, outside is called evanescent field. Evanescent field. So, evanescent field is field outside the waveguide core that is decaying exponentially with an attenuation coefficient or attenuation factor, right, given by alpha, and that alpha is nothing but k times n1 square sin square theta 1 minus n2 square under root, right. So, this is actually the attenuation coefficient. So, if you really want to know how quickly the attenuation happens, again we can do it here. So, let us say n1 and n2 both the directions, and this is 0 and we know this is d, right, and this is d by 2 and minus d by 2, let us say. The field we saw that it is going to be like this, right. So, here we have beta and here we have alpha. So, beta is the propagation constant that keeps the wave going through, alpha is the attenuation factor. So, how quickly the wave is going to decay. So, let us look at how this will happen, right. So, when x is greater than equal to d over 2, right, so in the upper side your field is nothing but E2 e to the power minus alpha x minus d by 2 e to the power I beta minus omega t. Similarly, for lower side where we have x less than or equal to d by 2 minus d by 2, your E is nothing but E2 e to the power of plus alpha x plus d over 2 e to the power I beta z minus omega t. All right. So, this is how you will have d electric field decay when it is outside the core of this waveguide. So, this is how you can confine the light. So, we talk about waveguides can be designed to confine light and propagate light. This is how we achieve that confinement. So, in N1 you have a solution that is oscillating, but then when it goes outside in N2 it will decay, and at what rate it decay is this alpha. So, you can look at the constituents of this alpha. So, it strongly depends on the refractive index, right, of the core medium and the cladding medium, right. So, if you want your wave to be highly confined. So, let me draw that, right. So, there are two waveguides, let us say, okay. They are all of same thickness, right, but then one waveguide you have a field like this, and for another waveguide you have a field like this. So, remember that your dimension is identical, right, but then one is having this and one is having that. So, now the question to ask is the decay alpha here. So, let me call this as alpha 1 and this is alpha 2. So, which one is greater? So, which one is decaying fast? Of course, alpha. So, alpha 1 is greater than alpha 2. So, how did we achieve this? So, this is achieved by looking at the refractive index contrast. So, N1 and N2, right. We can have refractive index N1 and N2 here. So, when the refractive index N1 is much greater than N2, you get very high confinement. That means you have very strong decay. So, the light is not allowed to go out, right. So, it is pushed inside, but in this case N1 is just greater than N2, it just meets the criteria. So, based on the refractive index contrast, one can actually decay the the light, the evanescent field that you have, right. And in some cases you may want to have this evanescent field stretch longer. We will look at this in our application, right. In some application we do want this evanescent field to stretch out, okay. And we can engineer this decay rate or evanescent field by looking at the refractive index contrast. Alright. So, let us look at another factor we define, right. So, we are talking about refractive index N1 and N2 and so on. The waveguide got its own refractive index, we call it as waveguide effective index. Waveguide effective index. So, let us start from our understanding of phase velocity. We know the waveguide phase velocity. So, phase velocity is given by omega over beta, right. So, this is the phase velocity. So, now if we say the refractive index. So, what is refractive index? So, refractive index is nothing but C over V, right. So, Vp in this case, right. So, this is refractive index, right. So, this is refractive index, but now what is effective refractive index? So, effective refractive index is nothing but N effective is nothing but C over Vp, right. So, here Vp is the phase velocity in the waveguide. Alright. So, in other words, let us try to expand this because this looks too trivial, there is something to this, right. So, this phase velocity is given by this. So, your Vp is nothing but omega over beta, right. So, beta is the one that dictates this. In other words, it says beta over k, right. And you can also write this in a more simplified form N1 sin theta, right. So, this is the effective refractive index. So, effective refractive index is a key parameter, right. So, effective refractive index is a key parameter in a guided propagation. And refractive index, right, refractive index that we talk about n1, n2, those are all refractive index in a ion guided fashion, right. So, n effective is actually applicable to propagating mediums or guided medium. So, when you talk about any kind of waveguide, that it be slab or channel, you would actually ask for effective index of that medium, right. Since this is beta, right, we also saw that this beta is actually beta m, depends on the mode number, right. And if that is the case, n effective should also be a function of the mode. So, a TE mode, right, TE0 will have beta 0 and it will have n effective 0, and TE1 mode will have beta 1 and then n effective 1. So, each mode will have its own effective refractive index here, all right, and it will the wavelength inside this waveguide is also determined by this n effective. So, now the wavelength that we measure along z direction, right. So, now the wavelength, right, is now lambda here, right, along z is given by lambda over n effective. Okay. So, now with this effective refractive index, the wavelength would also change, and now this is also a function of a mode, right, that is m here. But again we know that your lambda, right, and your refractive index. So, the lambda is also function of whether it is free space or in the medium here, but this n effective, right, is related to n, right, and it is, and that is one of the reason why this n effective is also a function of lambda. Okay. So, all this is related to the dispersion that we already discussed quite in detail earlier on. Okay. So, effective refractive index is something key to our understanding, which we use to capture a lot of things here. So, we are with effective index, you are capturing the material property, the n, the refractive index, right, the bulk refractive index of the medium. We are capturing the lambda, the wavelength of light through k. So, it combines the physical properties and also optical properties of light that is propagating through this medium. So, effective refractive index is an important parameter that we use in quantifying light propagation in waveguides, all right. So, with that we have come to end of this waveguide understanding. So, we know how the light is propagating through and how we can understand the confinement of light and how the interfaces and the conditions are affecting the light propagation. So, in the following lecture we will look at the actual field profile. So, we will look at the field equation, and then we have drawn the Gaussian profile and also the first order mode and second order mode, but we will actually look at the Maxwell equation and the wave equation to look at how this mode shapes evolve, all right. So, thank you very much for listening.